last class we have taken non-portal frame. So this is a portal frame. Portal frames are, why it is different? It is a structure which is used for constructing many buildings. So in the last class I have discussed a frame. It is not a portal frame, so which consists of beam and column, and in similar way you will be having many number of bays with that. So let us take this kind of a problem. This will be frequently crossed by many of the civil engineers. And let us take this frame, and you have two columns and a beam which is having a uniformly distributed load 20 kN per meter. You should analyze the frame. What is analyzed is finding the bending moment and shear force. If required, you can find the slope and deflection. Now let us stick into this problem and find the bending moment for this case by using matrix stiffness method. Okay, there are certain steps which has to be followed for all the cases. This will not change. It is similar for all the cases irrespective of the type of your problem. Now step 1 is finding the fixed end moment. Since you don't have A and B, this span has no load, the moment is 0, and C to D the moment will be 0. You will be having bending moment at B and C. So in between these two joint you have a member with a load. So if you have uniformly distributed load, you will be having 20 kN per meter, and the formula is WL square by 12. For BC is minus and CB is plus. So this is the simple change, and you can find W. You can substitute as 20. L, the span is 6 meter, and it will be minus 60 kN meter and plus 60 kN meter. So since it is a non-sway frame, you can see that both the height of the column are same and both of the ends are same. You don't have any flexural rigidity change. The joints and connections are symmetrical, and if you cut this section into two half, both are symmetrical in y axis. These are the cases which has to be checked for sway or non-sway problem. So since it is a non-sway problem, we can go for the step 2, which is finding element coordinates. And what I mean by that is identifying the elements. Each and every beam is an element. So you have 3 number of elements, either beam or column, both are elements. So if you have 3 number of beam and column, that is A to B is 1, B to C is 2, and C to D is 3. So you have 3 number of elements, and you will be having 6 number of nodes. Why to find element coordinates is, see, this will give you an idea that how bigger is your problem, how lengthy or how complicated is your problem. By knowing this element coordinate, you have 3 number of member and 6 number of joints. At each member you will be having 2 number of nodes. By getting that, you know the size of the matrix. It might be element stiffness matrix and system stiffness matrix. You can get the size of your matrix. So this is element coordinates, and next step is finding the transformation matrix, that is beta. You have 2 number of betas here. Now you should find the indeterminacy. How to find the indeterminacy is, you should find the kinematic indeterminacy. What is Ki? Number of joints. How many number of joints are here? 1, 2, 3 and 4. You have 4 number of joints. So the formula is joints into 3. 3 is degree of freedom. So 4 into 3 will be 12 minus number of support reaction. So at joint A you have 3 number of reaction. At joint D you have 3. 3 plus 3 is 6. This is a partially hinged joint. Hence for a hinged joint you have 2 number of reaction that are vertical and horizontal. So the same way you have a reaction here, and this is vertical and horizontal. So 2 plus 2 is 4. So 4 plus 6 will be 10. So totally you will be having 10 number of reaction. So your formula is 12 minus 10, which will be 2. So these are the two kinematic indeterminacy. So now you have found that this problem has two kinematic indeterminacy, and what are they? One indeterminacy is at joint B and other indeterminacy at joint C. And if you have the first indeterminacy, the Ki now here is in rotational mode. You can twist this joint and it doesn't resist the moment. Hence, the mode of application of the load will be moment. What is the possibility of movement? That is, what is the possible kinematic indeterminacy? Is one rotation could happen at joint B and one rotation could happen at joint C. So this is Ki. Now you have two number of Ki, one is at joint B and one is at joint C. You have to apply a unit load at the joint B, and if you apply one here, how many element coordinates are there? There are 3 number of elements and you have 6 number of coordinates. You will be getting 0, 1, 1, 0, 0, 0. So this will be your transformation matrix, and for the next joint, if you apply one moment, you will be getting 0, 0, 0, 1, 1, 0. So you got 0, 0, 0, 1, 1, 0. So these two are your transformation matrix. Now you got beta, and beta is these two value which has to be summed up. Note that in matrix stiffness method you don't have B star and B naught. You only have a single matrix which consists of all the positive values. Okay. Now next step is to find force in element coordinates, that is fixed end moments. You have found out the fixed end moment for element AB. The bending moment is 0. From C to D or D to C is 0. You had a bending moment only at B and C. Yes, these two are your moments, that is minus 60 and plus 60. Rest of the elements are 0. So you have 0, 0, minus 60, plus 60, 0, 0. So this will be your fixed end moment. Yes, this is P naught, 0, 0, minus 60, plus 60, 0, 0. Yes. Now how to find fixed end coordinates, that is F naught is beta transpose into P naught. Now P naught you know here, and beta transpose you have to make column into rows. So you had the matrix like this. Now you have to make this first column into first row and the second column into second row. That is known as transformation. So you have made transformation here. Now multiply row into this column. You will be getting, this will become 0, 0, and third value is 1 into minus 60 is minus 60. And if you multiply this row and this column, you will be getting 1 into 60 as plus 60. Rest of the values will be 0. Okay, now your value you have got as minus 60 and plus 60 as F naught. Then F of F. What is F of F? Force applied at system coordinates. So you don't have any external force at the joints. Hence it will be 0, and your formula is F of F minus F naught is F of F is 0, 0, and F naught is minus 60 plus 60. So if you subtract, you will be getting 60 minus 60 as your answer. Now next step is finding the element stiffness matrix. How to find that? The formula is K1. K is EI by L 4224. Okay. Now you have 3 number of elements, that is element 1 is AB, BC and CD. You have 3 number of elements, and for each and every element you need to find element stiffness matrix. For K1 is for element 1. EI L is 6 meter and 4224 is written here. Now you can divide this 6 into each and every component. So 4 by 6 you can make it, and it will become 0.67. Same way you can divide 2 by 6 will become 0.33, likewise. The second member B to C also have 6 meter length. hence your K2 and K3 will be same. You can divide 6 into all the terms here and you will be getting 3 number of element stiffness matrix, and you can make into a single matrix. Only diagonal values will be active, rest of the components will be 0. If you substitute this value here, 0.67, 0.33, 0.33, 0.67. So this is your first matrix, second matrix and third matrix. Rest of the components will be inactive. Okay, now next step is finding system stiffness matrix. Your formula is capital K. Note that element stiffness is small k and system stiffness is capital K. How to find that? Beta transpose K into beta. Now you know beta transpose, first multiply into this K value, small k. First row into first column, you will be getting this is 0, 1 into 0.3 is 0.3 and rest of the component will be 0. Hence first value will be 0.3. Now first row into second column, you will be getting 1 into 0.67 as 0.67. Now first row into third column will be 1 into 0.67 is 0.67 and first row into fourth column will be 1 into 0.33 as 0.33. So rest of the component, if you multiply, you will be getting 0 values. The same way you multiply the second row into first column, you will be getting 0 and 0. The next of the values you will be getting 0.33, 0.67, 0.67, 0.33. So these values, first while multiplying beta transpose and K, you got this value. Now you have to multiply by this value into the P. Row into this column, first row into first column. So 0.67 into 1, 0.67 into 1. So totally if you are adding, you will be getting 1.34 and first row into second column, you will be getting 0.33 is written here and second row into first column will be 0.33 into 1. This is the only active component, hence 0.33 and second row into last column will be 0.67 plus 0.67. You will be getting 1.34. Now this is your K matrix. Okay, after getting this K, you have to find the system displacement matrix. How to find that? This is the component U, K inverse f of f minus f naught. So you have already found this f of f minus f naught, which is 60 and minus 60. Now you have to find K inverse. How to find K inverse? You have to interchange the value 1.34 and 1.34 will be here, and this diagonal sign has to be changed, that is 0.33 and 0.33 will be minus. Now you have to find the determinant. How to find determinant? 1.34 into 1.34 minus 0.33 into 0.33. This is your determinant here. So 1 by the determinant into the matrix inverse. Now you can find the system displacement by dividing. So if you multiply this and subtract, you will be getting 1.687 and if you multiply this row into this column, 1.34 into 60 plus 0.33 into 60, you will be getting 100 as your answer, and the bottom row 0.33 into 60, which will be minus, and 1.34 and minus 60, you will be getting the value in terms of minus. These are the two values and you can find the system displacement. If you divide this 100.2 divided by 1.687, you will be getting 59.406. Okay. Now element displacement matrix, the previous value, that is system displacement matrix into beta. So this is value row into this column. So you will be getting first value as 0 and this row into this column you will be getting 51.4 and row into this column we will be getting 59.406 and fourth row into this column will be minus 59, minus 59 and 0. This is the element stiffness matrix, and finally P dash, how to find is K into element displacement matrix. So multiply this value into this. So row into this column, you will be getting this value. That is 0.33 into 59.406 will be 19.604. Likewise, you multiply each and every row into this column. So 0.67 into 59.40 will be 39.802. Likewise, you can do it for the rest of the things. You will be getting P dash, and how to find final force Pf equal to P naught plus P dash. So P dash value you currently got here, and P naught is the fixed end moment. You can add all the value. So 0 plus 19.64 will be 19.604, and 0 plus this value will be same. Minus 60 plus 20 will be 39.802, and plus 60 minus 20.198 will be this value, and you can see that you got the final negative bending moment. And how to find positive bending moment? You can take it as a simply supported beam and find the moment, that is WL square by 8. The answer is 90. Now you can check that if you find the values at the joint B and joint D, joint C, joint B and C have similar values. Due to symmetry, you can see that at joint B and joint C, if you cut this section, you will be having two symmetrical values of bending moment. Because of structural symmetry, the bending moment is also symmetry here. And at the joint A, you got 19.607. This is the negative moment, and the positive moment is 90 at the loaded area. Now you can strike off the values, and this is your net bending moment. So by this steps, you can find the bending moment of a framed structure. You can observe here for this problem that the procedure is same. It does not change.